Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today, we are buckling up for a high-velocity journey right into the heart of rotating machinery design. For too long, the classroom really focused on this simple, clean world of two-dimensional flow analysis.
Right, the perfect world.
The perfect world. But the reality inside an axial compressor or a turbocharger or these massive hydraulic turbines, it's fierce, complex, three-dimensional storm.
Absolutely.
So our mission for this deep dive is to move past those, comfortable, simplified models and really get what engineers have to master to design machines that don't just work, but operate at peak efficiency.
And that's our core mission today, to unpack the compromises. We need to understand precisely where those early theoretical models, the ones assuming perfect, frictionless flow where they break down, because engineers aren't just balancing efficiency, they're balancing it against brutal real-world constraints. The expense of manufacturing, the aerodynamic limit of the Mach number, and the frankly terrifying reality of cavitation. We're going from paper theory to steel reality.
Okay, so we've got a deep dive laid out that builds this up sequentially. We'll start by establishing why 2D models fail and how engineers try to fix that with tools like radial equilibrium and free vortex flow. Then we'll move into more complex modeling with the actuator disk concept and the power and pitfalls of CFD.
Computational Fluid Dynamics.
Yeah, we'll look at high-speed compressor inlets, the advantages of inward flow radial turbines, and finish with the ultimate fluid challenge, water, and the physics of the cavitation limit. So let's start where most textbooks do. The ideal axial turbomachine. We pretend flow velocities are only axial and tangential. We just ignore any radial or span-wise movement. When is that fundamental 2D assumption actually justifiable?
That simplification only really holds up if you're looking at a machine with a high hub-to-tip ratio.
Okay, what do you mean by that?
If that ratio, the size of the inner hub relative to the outer casing, is greater than about 4/5, then the flow path is narrow enough that you can essentially get away with treating the flow as two-dimensional.
But the moment you drop below that 4/5 ratio, the complexity just explodes.
Yeah.
What's the physical driver that forces the flow into 3 dimensions?
It's a battle of forces right across the span of the blade. As the fluid moves through the rotor, you get these strong centrifugal forces that start pushing the fluid outwards towards the casing.
And what's fighting that push?
The only thing resisting it is the radial pressure gradient. So in a machine with a low hub-to-tip ratio, that balance is temporarily lost inside the blade row. The centrifugal force just momentarily overwhelms the pressure forces, and you get these appreciable radial velocities.
And what's the engineering consequence of that uncontrolled radial movement? What does it break?
Oh, it seriously messes up the system.
Uh,
It redistributes the mass flow, which means your outlet velocity and your flow angle distribution are just wrong across the radius.
so the next set of blades gets hit with completely messed up airflow.
Exactly. And that's catastrophic for the next blade row because it hits the blades at the wrong angle. It just shreds efficiency.
So to tackle this, engineers developed the radial equilibrium method. It sounds powerful, but you mentioned it relies on a couple of major assumptions to make the math easier. What are those shortcuts?
The first assumption is that any radial flow that happens is completely finished within the blade row. The second, which gives the method its name, is that the flow outside the blade row is in radial equilibrium.
Meaning the pressure forces and centrifugal forces are perfectly balanced again.
Precisely. Perfectly balanced once the flow is clear of the blades.
Now, within that framework, a design approach emerges. Free vortex flow. This is the theoretical ideal, right, where you aim for equal work at every radius. What's the mathematical definition of that?
It's defined by the property that the product of the radius and the tangential velocity, so r multiplied by CQ, must remain a constant. A constant, yeah. Sometimes you'll hear the term vortex-free, which is maybe more accurate because it really means the axial component of vorticity is 0.
And the big theoretical benefit, assuming ideal flow, is that this means your axial velocity, your Cx, is also constant with radius. Perfect. Balanced work. So what's the practical penalty for chasing that perfection?
Money and manufacturing difficulty. To get that characteristic, the rotor blades need a massive complex twist from the root to the tip. And that twist means you can't just cast the blade. You need these specialized multi-axis milling machines. It adds huge expense. Plus, that design creates really large fluid deflections near the inner wall, which is detrimental to performance. It's that classic trade-off. Theoretical perfection often means manufacturing impossibility.
That's a great example. And speaking of reality, experiments later showed that the radial equilibrium assumption was, well, it's flawed, especially in those low hub-to-tip ratio machines. Equilibrium is not established inside the blade rope.
Precisely. You can still measure radial velocities downstream. That fundamental disconnect led to the actuator disk concept. This is a brilliant theoretical step forward.
How does it work?
We stop treating the blade row as a thick physical thing, and instead we conceptually shrink its axial width down to a flat plane, a discontinuity, the disk.
And this model lets engineers use a key relationship, the mean value rule. What does that tell us about the flow at that conceptual disk?
So the mean value rule says that the axial velocity right at the disk, let's call it Cx0, is equal to the average of the axial velocities far upstream and far downstream.
Okay, the average. Why is that so critical?
It's critical because it lets us model how those velocity perturbations that start at the blade row then decay exponentially as you move away from the disk. It captures the non-equilibrium transition that the old model completely missed.
Actuator disk theory provided great insight. But as machines got faster and more complex, engineers had to embrace pure computational power, CFD. Before modern CFD, what were the early workhorse methods?
The streamline curvature method is the oldest, and it's still widely used. But we also saw finite difference solutions. And for high-speed transonic flows, where you have shock waves, time-marching methods became essential.
So what's the role of modern CFD now? Is it just about modeling the flow more accurately?
It's far more strategic than that. Modern CFD allows designers to actually exploit the three-dimensional nature of the flow. Instead of just tolerating the 3D complexity, we can use it.
Use it how?
We can design blade shaping to actively suppress or mitigate things like corner stall in compressors or the strong secondary flows that just eat up efficiency in turbines.
That sounds like a magic bullet. But you often hear experienced designers warning against over-relying on the computer. What's the human insight that has to come before any CFD analysis?
The insight is this. CFD is a refinement tool. It is not a foundational design tool. If your preliminary one-dimensional design is fundamentally flawed, if your velocity triangles are wrong, no amount of CFD is going to save the machine.
Garbage in, garbage out.
Exactly. You must begin with sound physical understanding or you just get pretty pictures of a bad design.
Let's pivot to specific machines then, starting with compressors. Centrifugal compressors powered early jets, but were eventually replaced by axial types for large aircraft. Why was that?
Mainly due to the axial machine's smaller frontal area and higher efficiency. But centrifugals are still the undisputed champions for applications that need very low air mass flow rates.
Like a turbocharger on a car engine.
Exactly like that. They're robust, compact, and give you a lot of pressure rise in one go.
So whether it's an air compressor or a liquid pump, the inlet eye, the entrance to the impeller, is critical. What are the two main physical limits designers are always fighting against right there?
Both limits come from high relative inlet velocity. In a compressor, that high velocity leads to high Mach number losses, which crushes your efficiency.
In a pump.
In a pump, that same high velocity causes the local pressure to drop, which can trigger cavitation.
So for an incompressible application, there's an ideal geometry for that inducer tip to get maximum flow. What angle are designers aiming for?
The analysis shows that the optimum relative flow angle at the inducer tip, which we call beta S1, typically lies in the range of 56 to 60 degrees. That's the sweet spot.
To handle the high Mach number problem in compressors, engineers introduce what's called positive pre-whirl. They use guide vanes to spin the flow in the same direction as the impeller. What's the big trade-off that comes with that?
Pre-whirl is fantastic because it significantly reduces the relative inlet Mach number, fewer shock waves, fewer losses. However,
There's always a however.
there is. If you look at the fundamental work equation, the specific work done on the gas is inherently reduced by that pre-whirl.
So to get the same pressure ratio.
The only way out is to increase the blade tip speed. You have to spin the hardware faster. So you save the aerodynamics, but you pay for it with increased structural stress and mechanical challenges.
Okay, now let's reverse the process and look at radial turbines, specifically the 90-degree inward flow radial, or IFR, turbine. These are common in things like turbochargers and small gas turbines.
Right, and their key advantage over an axial turbine becomes really clear when you break down the specific work equation. We find that the largest contribution to specific work comes from the centrifugal action term,
Which is?
That is 1/2 multiplied by the difference between the square of the inlet tip speed and the square of the exit tip speed.
And that term is, of course, 0 in an axial machine because the inlet and outlet radii are the same.
Exactly. This term is what gives the IFR turbine its punch. In some examples, that one term can account for almost 38% of the total specific work. It's the core mechanism for high work extraction.
Now for the performance surprise. For decades, designers assumed the nominal design meant aiming for a 0 incidence angle at the rotor inlet. They thought the relative flow should be perfectly radial when it hit the blade. What did research reveal?
Reality threw the textbook out the window. Research showed that the condition for optimal efficiency occurs at a significant non-zero incidence angle, often between 20 and 40 degrees for radial vanes.
Wait, hold on. So for decades, designers were aiming for the mathematically simplest entry point, but they were actually leaving huge efficiency gains on the table.
That's the surprise. That high non-zero incidence angle is physically necessary. It correctly locates the inlet stagnation point on the vane leading edge, and it lets the fluid smoothly negotiate the complex rotational effects into the passage.
And the theoretically simple 0 incidence flow.
It ends up causing flow separation and massive losses. It's a perfect example of 3D effects just completely overriding 2D intuition.
Let's shift away from gas and look at water flow hydraulic turbines like Francis or Kaplan turbines. These things can achieve efficiencies up to 95%.
They're engineering marvels. But the defining challenge for any water-based machine is cavitation. This is the spontaneous formation of vapor bubbles when the local static pressure drops below the water's vapor pressure.
And we know cavitation is just devastating. It causes severe vibration and can literally erode solid steel blades. How do engineers quantify and predict that limit?
They use the Tama coefficient, designated by the Greek letter sigma. This is the crucial design metric. It directly correlates the net positive section head, or NPSH, with the available effective head, HE.
Let's quickly define NPSH. In simple terms, what is that?
NPSH is simply the available pressure margin you have above the point where the water physically starts to boil into those destructive bubbles. If your turbine's operating sigma is less than the critical value, sigma cavitation is inevitable.
So given that limit, what's the key strategy to avoid it, especially in, say, a huge dam installation?
The only way to guarantee safety is through physical placement. The turbine has to be located low enough relative to the tail race water level
To keep the pressure up.
to keep the pressure up, exactly. And crucially, the greater the head, HHE, that the system is exploiting, the lower that turbine must be submerged to suppress bubble formation.
And finally, let's talk about the violence of this. The vapor bubbles collapse. How violent is that, really?
The collapses, it's almost unimaginable. It's so rapid and localized that it generates shock waves reaching 4,000 atmospheres.
4,000 times the pressure of the air around us.
That's right. The process is called sonoluminescence, and it's so violent it produces brief flashes of visible light. They've actually seen light in the tail race of high-energy installations like the Boulder Dam at night.
Wow. That's why steel and concrete just disintegrate over time.
Yeah.
That kind of violence is staggering. We've certainly traveled a huge distance today, from the flaws of 2D modeling to these brutal physical constraints.
We really have. We saw the need to move past simple 2D models with the axial equilibrium method and how the actuator disk concept better captures that non-equilibrium zone. We identified the huge work advantage of the IFR turbine from its centrifugal term and the surprise that optimal efficiency needs a highly non-radial flow angle. And finally, we looked at the non-negotiable limit of the Tama coefficient and cavitation.
Thank you for joining us on this deep dive into the philosophy, physics, and hard constraints of rotating machinery design.
And here's a final thought for you to carry forward. We talked about CFD and its power to model these complex 3D flows. But remember that while CFD can design highly optimized blades, predicting the subtle, complex, viscous losses like turbulence generation remains one of the most difficult areas in all of engineering physics.
So when you're faced with two competing CFD models for a new blade, both showing near-perfect efficiency, but one models turbulence slightly differently than the other, why is the human judgment of an experienced engineer the one who can mentally map the fluid physics onto that data? Why is that always going to be the most critical factor in achieving true peak performance in a physical machine? Something to consider until next time.